Okay, welcome to part 2 of my visualizing developmental data workshop that was supposed to be at SRA 2020. This recording is happening about a month after part 1. I hope everybody's keeping well at home and staying safe. And in the off chance that any of you are going to still find this useful during our quarantine period, I wanted to complete the videos and make sure that you had what you need. In this section, we're going to work on visualizing age trends in fitted data. Plotting fitted data is normally what we think of when we are planning to plot the results of our model. So I've got two kinds of plots I want to go over. First are fitted trajectories that we would obtain for individual participants in a sample. And this is a version of the spaghetti plot we saw in the first video, but we're working with fitted data instead of raw data. A second type of fitted trajectory is for the sample means and group means. So these are primarily of interest in plotting results, and that's what we tend to refer to as the trajectories that result from our analysis. We often plot the sample mean trajectory or plot the trajectories of people who are, say, high and low on some change predictor, like in the current example, family cohesion. So what we're going to add here is a way to plot these trajectories with confidence bands around them. And I'll explain a little more about that in a couple of slides. First, let's just briefly look at the model that Chen and Harris fit in their paper that we were using as the motivating example with the complete AdHealth data. These are just some screenshots from their manuscript. So we can see that they estimated an unconditional cubic growth curve. That's what we're seeing here as Model 1. And Model 2 added a number of predictor variables, including family cohesion, and they say to examine whether the initial level and slope of depressive symptoms varied. So that's a question, that's an interaction question, a predictor of change. This is the unconditional model that we fit to the data for the purposes of this example. I've got depression at ages 12 through 29. I've depicted here. Those are the indicator variables in a latent variable growth model. Each of these is regressed on an intercept factor with a loading of 1. And that's capturing a conditional mean over all of the time points, all of the ages of depression. Each of these is also regressed on 3 additional growth slopes, 1 linear, 1 quadratic, and 1 cubic. In the case of linear, I've got integers separating each of the loadings. And if you're familiar with this approach, we square those linear loadings to get a quadratic slope, and then we cube them to get a cubic slope. So this is a polynomial model. So a couple of points here. A model with this many repeated measures often doesn't really work well as polynomial growth because a large number of time points tend to create a large number of opportunities for misfit. So I have the linear slope loadings going from -9 to +8, which gives me an intercept at about age 21. This decision is normally pretty arbitrary. You can kind of have your growth starting at the beginning. You could have it have your 0 loading at the end or anywhere in the middle. But in this case, knowing that I'm going to have some cubed loadings, I wanted to keep the number of very large values on those cubic slope loadings down. So placing an intercept in the middle facilitated that. So I've got in red here the results of this particular model. So each of these red estimates is the mean parameter for each growth factor in the model. So you should be able to run this model in your own preferred software and get the same results. So this value 0.442 is the expected value of the intercept at age 21. So mean depression at age 21, and these are the rates of change in linear, quadratic, and cubic terms. So I've included some M+ output in the folder for this presentation for you to look at, but you can do this yourself in any software. I've also included a data file that contains the predicted values that we'll be using to make figures going forward, so you don't have to construct those yourself. Okay, so the first plot we're going to do is a spaghetti plot using the fitted trajectories for individuals. So, okay, why would I want this? Any growth model that you run that has a random intercept and one or more random slopes for age is going to have some vertical variability in the level of the outcome, and also some trend variability in the steepness or shallowness of the lines that correspond to each person's fitted trajectory. These can be really useful diagnostic tools for growth models, these sorts of plots. So is that model fit providing a reasonable visual approximation to the raw data? You can ask that by comparing it to your raw spaghetti trajectories. Is there any meaningful random slope variability in your data? You can always check that with likelihood ratio tests, but with large samples, those can be overly sensitive. So it's nice to be able to actually see whether people's slopes are varying. And in this case, you can see there seems to be quite a bit of variability in these slopes. If you had something like a growth mixture model, how similar and different are the individual fitted trajectories within and across classes? That's something that's worth inspecting with your eyes. And then how much uncertainty is there at each age around your fitted mean trajectory? That's something that you can see a little more easily with these individual lines. This isn't necessarily a plot that's going to make its way into your manuscript, but it should definitely be a diagnostic step that you undertake when you're trying to fit a model. You might also want to use it as like the underlay in a plot that has fitted trajectories for groups or for means. The same way we had our points, our scatter plot underlaid and sort of partially transparent. Most software that fits growth models also includes a way to extract individual predicted values. And that's the data that we're going to use to make plots and show how expected levels and rates of change differ across individuals in the sample. Okay, let's see how to make a plot of fitted trajectories in R using ggplot. First, we're going to need to go get the data that contains those fitted trajectories for each person. So I'm just going to call that data set predicted. Remember, this is just the name of an R object that's going to contain, in this case, data. And I'm going to use read.csv to get my CSV file. Remember, you can do file equals file choose if you want, and that will open up a file picker for you. In my case, I've got a working directory ready to go. So I'm just going to call up the file by name. I've got predicted LCM data.csv in my folder. Okay, so that is ready to go. I can see it in my environment here. I can view just the first little bit of it with the command head, followed by the name of the data set. It's one way to quickly look at it. So I've got an intercept I, slope S, quadratic term Q, cubic term C for each person. right? There's ID1 for rows, and a value for family cohesion, the binned version of it, our two age variables. There's a centered version of age, there's a binned version of raw age, and a predicted score, right? Pred Y, that's my predicted score at each time point for each age for each person. We can just reuse the code we used before for making a spaghetti plot. There's really nothing new here. So I'm going to go ahead and copy and paste the relevant content from earlier on in our code here. I'm going to go right back up to, there's my spaghetti plot. Okay, copy that, bring it down, and give it a new name. I'm going to call it fitted. Okay, now we're going to use a different data set for this. I'm going to want to use the one we just brought in, predicted. Okay, and then my Y variable isn't my observed depression score anymore. It's this predicted variable, pred Y. That variable name is going to depend on your software, what name you've given something if you've constructed a data set. I'm also going to go with age bin for my x-axis, so I can see the actual ages rather than the centered age I used in the model. So I'm using geom line as before, a grouping variable ID in my aesthetic statement for geom line. And let's increase the opacity to say 0.4 and put some color onto those lines. So I'm going to go with royal blue 4. My scale, I still have depression as the y-axis, and I still have this same range of 0 to 3 that I want to stick with. And my x-axis age goes from 12 to 30. And this bit down here, this was just my theme that I constructed, if you recall from a previous video, so I'm leaving it as is. Okay, so we can run the first part of this. You can literally click anywhere in this code and command return to run the plot, and then render it by calling up the name of the object. And there it is. Now, if I can sort of squish that down to make it a little closer to what we saw in the slides. I'm also noticing that the y-axis has been restricted. It only goes to about 2, even though I want it to go to 3. So I'm going to have to add those limits. Limits equals concatenate statement 0 to 3 to force that y-axis to go beyond the range of the observed data. Run that again, render it again, and now I've got my y-axis all the way up to the limit of my observed data. So you can play around with the transparency level of your geom line function, because you might want to be able to see more of the lines on top of each other. If I go down to 0.2 instead of 0.4, for example, I can see a few of these in the lower range a little bit better. Okay. Now remember, because we're not just relying on a single data set for every plot we can mix and match, here's a great opportunity for us to just go ahead and add those raw means that we collected from, that we constructed from an earlier step directly into this plot. So I can make a new fitted plot. Let's call it fit with mean. And I'm just going to add it directly to this one. So start with fitted, the plot I just made. And I'm going to add geom line. Remember, we did this before. Could literally just go back up and copy it. In fact, why don't I do that? This was from, this one right up here was when we did it for 2 groups, but we can keep scrolling and go find it for, oh, here it is, sort of inside of another plot. Geome line and geome point. Okay, so I'm referencing that data set depth means that we created in the previous video. Mean depth was the y-axis, age bin was the x-axis, and I controlled the size and the color, and we also made points as well, because that's my personal aesthetic preference for how to view plots of means over time. Okay, so I'm going to run the plot command and render the plot. And there we go. So you can see it's just overlaid the means directly on top of the fitted. Okay, so this is the sort of diagnostic plot that you might use to, figure out whether the time trends that you're imposing on your data make sense. And at some point, you're going to want to move on to modeling, and so that's the kind of plot we're going to look at next, plotting our fitted trajectories with uncertainty estimates around them. Okay, I'm going to spend the bulk of our time talking about building confidence bands for your trajectory plots. So this section is primarily about graphical uncertainty, right? We don't do this enough. Every line that you plot has some degree of uncertainty around it, and areas that comprise more data, right? More data that underlies a trajectory is going to be more precise than an area with less data. We're really just used to reporting parameter estimates like the intercepts and slopes, but we're less used to presenting the uncertainty information around those parameters. So I have a figure on the slide here that I pulled from a fairly recent paper in the Journal of Research on Adolescence, which is our society's journal. They used a model using the time varying effect modeling software that incorporates confidence bands by default. So we can see there's a couple of different plots here, just focusing on the top line. I've got a plot across age of the strength of an effect of sensation seeking on odds of past 30-day smoking. So it appears to be, your odds are higher with increases in sensation seeking, and that's great. That's as expected, but we can see that this effect is, seems to be stronger at younger ages and sort of weaker in this middle portion between about ages 20 and 25. But this is the fitted line, right? The solid black one. And the dots show me the confidence interval around all the points on that line. This fitted line has the widest confidence region at the youngest and the oldest ages. So that's where we have the least amount of data and the lowest precision. So the trend lines are, this is sort of furthest away from an odds of 1, but our confidence interval is also pretty wide there, so we are less certain about that rating once we're sort of sneaking below age 15. We have an effect that we think is strong over here, but we have poor evidence for it because of a large confidence interval. Also, we can notice that once we get to about, age 32 or so, this effect of sensation seeking has a confidence interval that overlaps an odds of 1. So this effect is not statistically distinguishable from null, despite the fact that the fitted line, so per parameter estimate is still pretty high. So that's pretty important information to have on your plot, that would otherwise be hidden if you were just plotting the fitted line. So adding confidence bands to a fitted trajectory are really important for describing uncertainty that we have in the estimates of our growth model at every age, and it's going to help us narrow down where an effect is most meaningful. If you have a predictor of change, you might want to be plotting two lines, people who are high and low on some say baseline variable. And those confidence bands are going to allow us to tell the ages at which two groups or two levels of some variable are significantly different from each other. So, that sounds great. That sounds like important, useful, additional information. Why haven't we all been doing this all along? Not surprisingly, it's something that's just often unavailable or not clear to an end user how you're going to make your software produce those uncertainty estimates. So I'm going to show you how all of this works algebraically so that you can solve for your own intervals regardless of your growth modeling software. I also have a couple of links in the resource notes at the end that'll show you how to get interval estimates out of M+, which you can then save and bring into R or any other software package to plot your confidence bands without having to do any calculations. But people use a wide variety of software, so I think the most inclusive way to approach this is to show you how it's calculated and give you a means to perform those calculations. So we're going to just take a brief detour into ordinary regression to see how this works. If you have a simple one predictor regression model, here I've got a variable on the x-axis called helicopter parenting that appears to have slightly negative effect on academic adjustment at the end of student semester. So I can tell that from my regression table here. I have an intercept and a slope of negative 0.11. But using that regression table, I cannot tell you what the confidence interval is around any given point on this line except for the intercept. Right? The standard error for the slope all by itself, that's not enough information. The slope is only going to tell us about the angle of that line. It doesn't tell us about its position in vertical space. And that information matters too when we're calculating confidence regions. So I can get ggplot to put a confidence band around a regression line, and also some other packages and programs outside of R can do this. But I'm not aware of too many automated processes for doing this with growth trajectories. So it's pretty useful to understand exactly how this works when you're doing it yourself. Okay, so here's how we would calculate the confidence limits for the effect of helicopter parenting on academic adjustment at the intercept, but at no other places. We've all seen this before, right? You take your estimate and you add your cutoff value from whatever your test statistic is. In this case, this is a z-score of 1.96 multiplied by the standard error. Right, so I'm adding this quantity to the estimate. I'm also subtracting that quantity, and that gives me some limits on a 95% confidence region. And so this is great, but this is the precision of my estimate at exactly this point and no other point. Unfortunately, and I've done this on purpose, my observed data are only in this range, right, between these blue dotted lines. So I've got a confidence estimate for an effect that doesn't exist, right? There's no data out here. So, ideally, we're going to want some confidence regions for at least some of the points in the observed data range, but ideally all of them. So happily, I can actually calculate the variance or uncertainty associated with literally any predicted value at all on that regression line. I just need to go beyond what I see in the table of results. So if we say we have a one predictor regression, B0 is the predicted value of y where my predictor variable x1 is equal to 0. And a standard table of results will give me a standard error for this value of y, where x equals 0 and no other place. But suppose what I want is the variance or standard error of my predicted y, where x1 is equal to exactly 3.5. Well, I can get that. I just need a few extra values, right? I need the values of x that go into solving for predicted y. So I'm going to need that. I'm going to need to know which value I want, 3.5. And I'm also going to need a weight for the intercept, which is a value of 1. My intercept term has an implied 1 in front of it. And then I'm also going to need some variances and covariances associated with my regression weights. This is information that that exists in our regression, but we kind of keep it under the hood. We don't normally request it, but we can. This is information you can get from any regression. It comes from a quadratic form. So the variance associated with any predicted value of y is a function of sort of this matrix multiplication term. I need my weights. I need some weights for x, and I need a covariance matrix. Okay. This term in the middle is a matrix of coefficient variances and covariances that's produced by our software, and those bolded x's on either side represent the weights that we need to apply to the coefficient variances and covariances. So here, for example, there's my one predictor regression results, and this is the asymptotic covariance matrix that is associated with this one predictor regression, right? A couple of those values we already know, right? The diagonals of this matrix are just the squares of the standard errors. In fact, this matrix is where those standard errors come from. What we don't normally see in default output is the off diagonal element. They do contribute to model error though, and they need to go into calculating a confidence band. So once we know that matrix exists, we're just going to multiply the elements of it by whatever weights that we selected for our predictors to get some single point variance estimate. If you haven't seen any matrix algebra before, you absolutely do not need to know it right now to follow along. I'm going to gloss over the details of how this works out, but most grad stat textbooks have an appendix at the back explaining matrix multiplication, and there's also a link in the resources section at the end of the slides to a 5-minute instructional video showing how matrix multiplication works. But just briefly, here's what we have. We've got our 3 elements that need to be multiplied. I want the variance of my predicted y at exactly a point associated with these regression coefficients, right? I've got a 1 for the intercept, 3.5 for the selected value of x. There's my asymptotic covariance matrix next, and there's my regression weights again. They're transposed into a column format in this case. Okay. There's the value of x, right? This entire matrix operation, if I multiply all 3 of these blocks together, I'm going to get a single value. This sequence will reduce to a single value, 0.0083 in this case. And if I take the square root of that value, I'm going to have a standard error. Okay, so this calculation gives me a variance, and the square root of my variance will give me a standard error. So 0.091 is the value that we're going to carry over into the next slide to make a plot. Okay, so now that I know that value, we're going to figure out what the confidence interval is around my single point. So I've got predicted y. Well, I can calculate that by taking my regression coefficients, right? My intercept 6.21 minus the coefficient for the slope 0.11 multiplied by the value of x that's of interest. In this case, is 3.5. So my predicted value is 5.83. And my standard error, I just calculated it on the previous slide. We know it to be 0.091. So now I just plug those values into my calculation for upper and lower limits of my confidence band. And those calculations will give me the limits that are shown in this purple line. So notice here that this region, right, this confidence interval is much tighter, and that makes sense because there's actually data over here, whereas there was no data over here where the red confidence interval came from. So 1 point is great, but ideally what we want is all of the points, and we want to see a band spanning the entire regression line. That's going to give me all of our uncertainties. So we're not going to hand calculate a point-wise standard error for the entire range of the x-axis. We just use the tools we have to automate those calculations, and we can simultaneously get enough points that we can draw a band connecting the dots and showing us uncertainties at all of the points on any particular fitted line that we care about. So what we're going to do is try this in R using our simulated add health data example. What I'm showing you here is a table of the fixed effects that came out of our growth model. So I showed these a few minutes ago on our path diagram slide. So these are the fixed effects that we care about, and these are the asymptotic variances and covariances associated with those fixed effects. So the diagonals correspond to squared standard errors, same as they did in the previous example. I've included this matrix as a small CSV file with our materials so that you can work with it directly here. This is not something you have to calculate. This is something that is going to be output from a piece of software, and that's a different command in different types of software. I've included some information in the resources section about how to go and find this for your particular software package. So from what we want to do this time, we don't want a single point. Remember, we want a whole bunch of points. We're trying to take our matrix of growth model loadings and try to come up with a vector of predicted value variances, right? We don't want a single variance for just one of the ages. We want a variance for every age. So we're going to need a vector containing a whole bunch of different variances. So I've just sort of shown this in part for some of the ages. Remember, these are our loadings for our intercept term, linear term, quadratic term, and cubic term. So I've got a whole bunch of these, one for each of our ages in the model. And what's going to happen here is that we're going to multiply across several terms and come up with values that correspond to each age, uncertainty at each age. So this matrix multiplication is going to result in not a single value, but a whole matrix full of values. And that's what's contained inside these parentheses. And we're only going to want to save the diagonal elements that result from that matrix multiplication. Okay, so we're going to be seeing something like this, right? For each age, we're going to want the elements that result from multiplying the loadings for that particular age by all of the elements of the covariance matrix and multiplied again by the loadings for a particular age. We're going to want to save the single number that comes from that series of multiplications. That's a diagonal element. We're going to keep it. Here's another one. We're going to want to save the element that comes from multiplying this row, right, the next age, by the covariance matrix and by this row. That's another diagonal element. We're going to keep it. but these are the parts we're not going to save, right? I'm not going to save the element that results from multiplying this row of loadings for a particular age by the covariance matrix by a non-matching row of age loadings. Okay, that's an off-diagonal element. It's going to be discarded. Okay, so you kind of get the idea of what's happening here. There's lots of multiplications happening, and we're going to save the subset that corresponds to variances at each age. So let's turn over to our software now and see how this works. Okay, so we're going to build those confidence bands, or build a confidence band for the mean trajectory of depression from our cubic growth model example. It's going to be, I've sort of listed it here as a 7-step process. We have to sort of create those matrices that need to be multiplied together. We need to save certain parts, and we need to combine it all together. So we'll start with the first step. I'm going to need to make a matrix that contains the growth factor loadings, right? Those are ones for the intercept, -9 to +8 for the linear slope, and so on for cubic and quadratic. So I'm going to make that. It's just another R objects. So I'll call it loadings, and I'm going to make this from a data frame statement. Okay, so there's a few different ways for you to create a data from scratch. This is a good one. I'm going to start by making an intercept, call it int, and it's going to contain, use that concatenate statement. It's going to need 18 entries. We're going from ages 12 to 29, so I'm going to need a row for each of those ages. So I'm going to repeat the number 1 18 times, and that's going to give me my first column in this data matrix. Next thing I need is a linear slope. We'll just call it SLP, and again concatenate. We're going to stick things together. This case I don't need the same number repeated a bunch of times, but I do need a sequence SEQ, going from -9 all the way to +8 by units of 1. So this will build a sequence of numbers consistent with my loadings. So I'm going to stop right there for now because the remaining elements are functions of that linear slope. So I can run this statement and create a loadings object. You can see that that's showing up here, right? 18 observations, 2 variables. Now I'm going to add 2 variables to this data file, this data object. So loadings, use the $sign to refer to a specific variable. I'm going to make a new one, $quad. What does that one get? Well, I'm going to take the variable I already have, loadings $slope, and I'm going to square it. Okay. And if I run that line, you'll see over here, now I have 3 variables in my loadings file. I just made a new one. I'm going to do the same thing again, loadings $cube, all right? Also based on loadings slope, and I'll cube that one. And now I'm up to 4 variables. Okay, and if I print loadings, we're going to see that we have an 18 row by 4 column matrix of loadings that are exactly what were in the actual model that we ran in M+, so that you would have run, if this were your own analysis. Okay, so step 1 down, we have that matrix. Well, I'm going to add one more step here. R currently isn't recognizing this object as a matrix object. It's recognizing it as more like a data object with variables that I can reference and manipulate. So I'm going to just change it. I'm going to call it my X matrix, and I'm going to tell R to read it as a matrix. Okay, and then if I just call that up, so I'll run that line, X matrix, so a new object called XMat as matrix, and then enter the previous object name. Run that, and then if I just call up XMat on its own line, it'll spit it out again for me. Okay, it looks really similar, except along the left-hand side, we have some matrix notation here. It's telling me I'm in row 1, row 2, and so on. Things contained in those square brackets are referring to matrix elements. Okay. Step 2, I need to get that asymptotic covariance matrix. So I've provided that for you here. We're going to go call it acov, and it's a new object again. And I've provided it as a CSV file, so you can read CSV. The file name is acov.un.csv, because this is the one from the unconditional model with no predictors. A couple of changes I want to make here. I want to get rid of the header line. Header equals false. I don't want it to contain names here or a row with identifiers. That's going to make it a little more difficult to multiply. And I'm going to give those rows some names that I can refer to. Okay. So my column names are going to be I, S, Q, and C. So just to clarify, header equals false is in there because there is no row containing variable names, right? This is just a 4x4 matrix of values currently contained as a CSV file. Okay, so I've run that, and now I can just print that guy out, and it'll show it to me in the console here. I'm looking at it in scientific notation, right? These asymptotic covariance matrices often include really, really small numbers, and those are more compactly expressed in scientific notation. So I've got the significant digits and an indicator of how many decimal places over I am. Okay, I also need to make sure that R is recognizing this as a matrix format object. So I'll just call this one cov_b now, using the other typical name for an asymptotic covariance matrix, and use the as matrix command. And then call up that new object, and now you can see it's got the same notation that the loadings object had. So now we've got all three of the things that we needed to perform that matrix operation, right? We have the data matrix, the covariance matrix in the middle, and then the data matrix on the other end, but transposed. So we can take those things and ask for them to be multiplied together, and then save the diagonals, and that can all happen in a single step. So I'm going to make, we know this is going to turn out to be a vector, right? I had 18 ages going from ages 12 to 29. And I'm going to need a standard error for every one of those ages, and that's a total of 18 different ages. So my vector object, SEY, I'm going to need to, well, let's start in the middle and work outward. So I'm going to multiply a bunch of stuff together. XMat, it's going to need to get multiplied. Now I can't just use this guy, right? I've got to use matrix multiplication. So I'm going to use %, asterisk, %, to matrix multiply my XMat matrix by my cov_b matrix by my XMat matrix again, but it's not the same one. I'm going to transpose it. So I go T for transpose, T XMat. Okay. So So those three things are getting multiplied together. But I only want to save the diagonal elements of them. So I'm going to go out here and use the diag function and put some parentheses around that whole thing. It's going to be a bunch of parentheses here. So this is now going to take just the diagonal elements of what is resulting from multiplying those three matrices together. And if I save those diagonals, I'll have a vector of variances, but I want standard errors. And so I need to do one more thing here, which is to take square root of all of that. So there's a new parentheses symbol and add another one there. So starting from the middle, working out, we should end up with now a single vector containing 18 standard errors. Okay, I'm gonna run that line, and I can see that right up here. It's values, SEY. It's a numeric vector going from elements 1 to 18, and here's the first set of numbers in that place. Great. I can also print it if I want. Okay. List of values. I can see the standard errors and how they're changing across the ages. Some ages are more precise than others. Okay. Great. I've got those standard errors. Now, if I want to get some confidence limits, I'm going to need to add them and subtract them from the predicted values at each age. So here's where I can bring in the fixed effects and calculate some predicted values. So sometimes this is easier to do by trying to save the predicted value or save the results directly from the output. Depending on the software that you're using, that's going to be more or less of a hassle. In this case, we just have 4 numbers, right? We have a fixed effect for the intercept, linear, quadratic, and cubic slope. So I'm just going to type them out here for simplicity. So my fixed effects, I'm going to use the command rbind for row bind. I'm going to row bind these into a column of 4 numbers, okay? Binding them row by row. So literally going straight back to that slide that contained in red the fixed effects, I'm typing them out here one by one. So my intercept was 0.4419. My linear slope had a value of negative 0.02258. My quadratic slope, even smaller, negative 0.00002614. And the cubic slope had a positive value of 0.0003176. Okay. Run that line and then ask to see those fixed effects. And there I have it. And it's already in a matrix format. The rbind command is referring to a matrix operation. So I've got a single column vector containing these 4 numbers. It's automatically placed it in scientific notation because I had some numbers with a large number of leading zeros. Okay. Now I've got everything I need to actually calculate a predicted value at each of my ages. This is again something that you might already have ready to go, especially because you can save predicted values, but I don't actually want predicted values for every single person in my data right now. I just want a candidate predicted value for each of the ages in the plot. So let's make predicted y a new object, and I just need to multiply my loadings, my 18x4 loading matrix, that was called xmat, matrix multiply it by the fixed effects. All right, I've got an 18x4 matrix multiplied by a 4x1 matrix. And then that'll give me an 18x1 column vector of predicted values. And if we print that guy out, you can see them right here. So here are the predicted scores at each of the ages. All right, and there's one over here It corresponds exactly to the value of the intercept as it should, right? That was the predicted value of depression at age 21. This should be age 21, right? Predicted values are a little bit different at all of the other ages. All right, now I've got everything I need to sort of create a data frame that includes the ages I want on the plot, the scores I want on the x-axis, and the confidence limits around each predicted value. So I'm going to build a new data file. It's another R object. We'll call it age data. And I'll use that data frame statement again. This is not normally how we would merge things together. It works in this situation because we know we have a small number of things and they're all ordered correctly. We don't have to worry about merging things on key variables at all. Normally, you would merge data sets with a different function that allows you to control what's getting lined up where. So start with making age. Well, we know age is going to be another sequence, right? Sequence starting at 12 and going to 29, incremented by 1. We cut off age 30 in the predicted values because there was too few observations there, and it was sort of distorting our fitted trends. Okay, so from 12 to 29, depression, that's our outcome. That's just going to be equal to the variable we just made, pred y, right? Our predicted values. And we need a standard error, and we'll just pull that from the vector that we just calculated from those earlier steps. Okay, so if we run this guy, we now have a new data set up here containing 18 observations and 3 variables. And we can use that to calculate my upper and lower limits. So if I want to make age data lower limit, right, this $ is saying, inside this data set, I'm going to add a new variable, right? $LL. That's my new variable name, lower limit. Start with the fixed effect, right? So my predicted score, depression. The lower limit is going to be subtracting my critical value, 1.96 times the standard error, age data SE. Okay. And same thing for the upper limit. In fact, you could copy and paste this and just change the minus to a plus. So I need my predicted score for depression plus my critical value, 1.96 times the standard error. If I run each of those lines, my data set gets bigger by 2 variables. I'll use this head command so we can just see a quick printout of what all is in there. Okay, in the console we see age, depression, predicted score, standard error, and the lower and upper limits. Now I literally have everything I need to make my plot. Okay. So we can copy and paste another plot to do this, but let's just start from scratch. Make a banded plot. Let's call it band, ggplot. We're using this new file, age data. And in the aesthetic statement, we want y to be depression, x to be age. Add a new line. Here's what we're going to do to get those lower and upper limits. Geom ribbon. Okay. Aesthetics. What is in the ribbon? Well, it's pretty intuitive. I need a y min. I need a minimum value for the bottom of the band. And that's going to be the value from the variable LL, right? My lower limit we just made. And y max is going to be the upper limit. Great. Okay, so now R knows, ggplot knows where the band's located. We can add a little bit to this. We can tell it to fill it with a particular color. You can fill it, so gray seems to be the default for a lot of things. We're going to go with that, but you can fill that band with any color you like. I'm going to go with gray 85. And I'm also going to control the transparency of that and not make it perfectly opaque. Okay, so that's the ribbon. All right, that's the bands. I also want the fitted line. All right, I've got geom line. I don't need to say anything special. It's just going to make a line out of the inherited values that we see up there in the ggplot command. And let's see. We're going to use our scale y continuous command to get depression listed on the y-axis, and we'll show a slightly smaller range of values this time. Let's have a limits of 0 to 2, and breaks going from 0 to 2 by values of 0.2, let's say. These are all things you can manipulate at your own discretion. Scale X, continuous again. So this one's going to be called age like it was before. Limits going from 12 to 29. And the breaks are going to be a sequence going from 12 to 29 by 1. I think I'm missing a parentheses there. And then we can apply our theme here. I'm going to copy and paste the theme that I've been using before. You can also create an object, an R object, just containing the theme lines to simplify things if you like passing the same thing through to multiple R plots. Okay, so that should be everything. Let's see if that gives me a plot I'm looking for. Okay, no errors. Now render the plot. Okay, there he is. Not very exciting. It's a single unconditional mean, and it was a lot of work to get there, but you get the idea here, right? I've got a band showing the certainty and uncertainty around the points at every age now. It's a little bit wider at the edges where there's less data. You can also modify this plot to include the individually fitted values if you like having that kind of overlay structure. So if I just go back and grab geom line from that fitted spaghetti plot we made before, I can add that here to our band plot. I'm going to have to be using a different data set, right? I'm going to have to go data equals predicted to get it drawing that data set that had our calculated predicted values from the full model. And I'm also not going to be able to inherit the values of y and x from that top line as well. So we can add those in here in our aesthetic statement. Y was equal to pred y, that was the label in that data set, and x was equal to age bin. And we want that grouping for ID on ID, so we have a different line for every person, and we can leave all the other things as is. Run that and render that plot. There you go. Okay, so after much effort, we have a fitted trend line with a confidence interval around each age overlaid on our individually predicted values. The last thing we're going to do is to modify those plot commands so that we can make more than one trajectory, right? A lot of the time you're going to have a predictor of your slope, and you'll want to see how two or more groups are changing over time. And we can get uncertainties for each of those groups and plot them in the same way. Okay, so this is going to look exactly like the steps that we went through for plotting an unconditional trajectory. And we can reuse some of what we've already done. So we had, remember we had one matrix of loading values for the 18 different ages, but that was just for a single line. We're going to need 2 lines, right? We're going to need a matrix of loadings for people who are low on family cohesion and for people who are high on family cohesion. And these are now coming from a model that had a predictor of the linear slope component. So we can construct that ourselves here. I'm gonna start with that loadings object we have, and I'm gonna make it into 2 new objects. One that contains information for the low trajectory and one for the high. I'm gonna start by making an object called low, and I'm just going to make it a copy of what was in the object loadings. Okay, and this object is going to now have a new element to our new variable inside it. I'm going to add cobin to it and assign cobin a value of 0. Right, so this is going to be my matrix of loadings for ages 12 to 29, and a vector of zeros to indicate that this is that this set of loadings applies to people who were low on family cohesion. Okay, and I'm going to make another object and call it high. It's also a copy of loadings, and high is going to get cobin at a value of 1. So then my new data set, or my new larger matrix of loadings, right, a set for high and a set for low, I'm going to call it famco, and I'm going to construct it by binding together the low object and the high object. Okay. Let's make sure I've run all of these. Okay. And then if I ask it to print out famco for me, here it is in the console. Oh, whoops. I forgot to add cobin to each of those. There we go. So here it is in the console. I've got my intercept, slope, quadratic, and cubic loadings, and then a new vector here, cobin, right, for the first 18 entries. It has a value of 0, and then we see the entire data set reproduce itself with a value of 1 for cobin. Okay, so now I've got enough information there to sort of identify which are the 2 trajectories. Now, we also want to make sure that we've got a column in there that picks up the interaction term between the linear slope and family cohesion. So we're going to add a variable to famco. We'll call it coslope. You call it whatever you want. And that's going to be famco slope, right? The set of linear slope loadings. Just multiply that by famco cobin. Okay. Oopsie, that's a $sign, not a asterisk. And then if I just print out the header there, now I can see that there's an extra column there, and that's going to have certainly zeros at this in this first block because cobin was equal to 0. Okay. So now I've got my data matrix contains 2 extra columns compared to the unconditional model. So we need the data matrix, we need the asymptotic covariance matrix. Let's go get that. We'll call it ACOV2. And I also provided you with this one. So that's another read CSV. And I called it ACOV-FC. So from the family cohesion model .csv. And again, header equals false because there are no header labels here. Let's give those columns some names. Column names equals, there's that concatenate function again. Let's go I, S, Q, C, and we have two more this one. We have ICO, that's sort of the intercept or main effect of COBIN, and SCO, the effect of COBIN on the linear slope. Okay, so that's 6 things that have parameter estimates and uncertainties associated with them. So I'm going to read that in and print it out to make sure it looks right. Here it is in the console. That's a 6x6 object. It's not being read as a matrix yet, so we're going to call it COV-B2 and ask for R to read that as a matrix. Okay. We should also do that for our loading data, right? XMAT2 as matrix. What did we call it? FAMCO. Okay. All right. So now we've got enough information to compute that vector of standard errors. Now we're going to have twice as many this time, right? We're going to have 18 standard errors for low family cohesion and 18 standard errors for high family cohesion, but the operation is the same. SEY2, again, I'll start from the middle and work out. So we started with XMAT2, XMAT2. This is a matrix. So matrix, multiply it by COV-B2 and then by the transpose of the matrix of loadings. All right, back that out. We only want the diagonal elements. So let's put diag and put some boundaries around that, make sure there's enough parentheses. And again, that'll give us variances. We just want to keep the square roots, so we have standard errors. So square root around all of that. And if I run this line and take a look over in the environment, I can see here I've got 36 elements, not 18. So I've got twice as many as I did last time. Print it just to see. And there are my 36 elements. Okay. Going to need those fixed effects again, right? Let's call it fixed 2. I'm going to do the same thing I did before. I'm just going to type them in. They're a little different, not very different, but a little different from the unconditional model. There's my intercept value. Here's my linear slope, 0.02, 458, 0.000215. That's for the linear growth model. And you can see these numbers in the M+ output that I've included with the materials for the workshop. 0.000285. That was for the cubic slope portion. And then I have negative 0.1184. There's my main effect of family cohesion. All right, higher cohesion, less depression. And here's the effect of family cohesion on the slope, 0.01278. All right, so that effect gets a little weaker with increasing age. And I'll just request that printout to make sure it's right. Okay, there it all is. Now I'm going to pull it all together in a single data set so I can make a plot. Age data 2, Again, use the data frame statement. I'll make age the same way I did before. Concatenate. Now this is a little trickier because I need ages going from 12 to 29 and then from 12 to 29 again, right? So I need it for the first half of the data, low cohesion, and then the second half. So I can kind of double something up here. I can repeat the sequence of 12 to 29 by 1, and I can repeat that a total of 2 times. Okay. Cobin. That's another variable I'm going to need so that I can say, well, plot this group of values for one category and plot the other values for the second category. So Cobin, I want that to be read as a categorical factor variable. So I'm adding as factor to the beginning here. And I'm going to concatenate a couple of things. First, I need to make a bunch of zeros for the first 18 entries. So that is repeat 0 18 times. And then repeat 1 18 times. Let's see. I need another. Make sure I've got the right number of parentheses here. We'll find out soon enough. Depression is going to be pred y2. The standard error is going to be that SEY2 that we just created. Okay. Let's find out if this makes a data frame. Oh, I'm definitely missing a parentheses somewhere. Let's take a quick look. That one looks okay. This one, I think it might be here. I got too many there. Oh, so we got to go back and make, forgot to make those predicted scores. I was trying to add them before they were created. Remember, we were multiplying our matrix of loadings by my matrix of fixed effects. Okay, now it's there, and now it's running. Let's just print the entire age data too. There we go, we got 36 entries. Okay, ages, those are repeated. They go from 12 to 29 and then start all over again for Cobin equals 1, right? And I've got a depression score and a standard error for each of those ages. Now we do exactly what we did before, which is to make a lower limit and an upper limit that we can use in the geom ribbon statement. Okay. Oops. Make sure we're referring to age data 2. That's our new data set here. Age data 2. It's going to be my predicted value depression minus critical value times the standard error. And we'll repeat that for the upper limit. And a plus, and call that UL instead of LL. Okay. Add those and check it with the header statement. And there they are. Okay. Now we can go ahead and make that plot. I'm going to copy and paste the plot we just made before for an unconditional model. Just going to comment out the individual lines here for now, so we can see the trajectories first. I'm going to use age data 2, same aesthetics because we haven't changed any variable names, And geom ribbon is exactly the same because we're still calling them LL and UL. The difference is we're going to need to add group equals cobin so that ggplot knows to make more than one ribbon, right? It's going to make a ribbon for low and for high. Okay. In geom line, we're also going to add an aesthetic statement and add color equals cobin and control the size of that line because we're going to want a separate color for each of our lines. And we had been using before scale color viridis. This is still a good choice. We're using the discrete option because there is a factor variable cobin that has exactly two colors, not a range of colors. And remember, you could choose a beginning point on that scale for colors and an ending point if you don't like the colors that appear by default at the beginning and end of the range. We'll call it name equals cohesion, right, for our label for the legend, and the individual groups, they have labels as well, low and high, in the order that they appear in the variable. I get that up here. Make sure we have pluses in the right places. And then everything else stays the same. Let's see how that turns out. Oh, it doesn't like that. Sometimes this one is solved by just highlighting the whole thing and running it. Yeah, that worked. Who knows why? Somebody, not me. Okay, and if I render it, here are my two bands. Okay. So what I've got here is a purple trajectory for people who are low in family cohesion and a green trajectory for people who are high. And what I've also got is a sense of where those two lines do and do not overlap, right? So if I was just looking at the fitted lines, I would say, oh, well, you know, these are sort of far apart initially and they kind of converge. But here I have more precision, right? I can say that these two longitudinal trends are significantly apart from each other, right? They're families that are low on cohesion are significantly more depressed than families who are high on cohesion, or children from those families are significantly more depressed as early as age 12, all the way up to approximately age 22 when they start to converge and become statistically indistinguishable. Right? That's information I don't have unless I have those uncertainties at each of my ages. Part of this has to do with family cohesion being measured early on in the study, right? So those time invariant predictors measured at baseline don't necessarily have the same level of discrimination all the way through a study. But at any rate, that's a take-home message I can communicate now that I have my bands around my two lines. And you can flush that out. Here, I'm just going to uncomment geom line here. You can flush that out by adding in my predicted data and the ID, the grouping ID. Can leave it as is, or you can take the color out and allow it to color along the scale that we were just using, right? So I'll go into the aesthetic statement and say color equals factor cobin. Okay, remake that plot, and there we have it. So now you can see the purple trajectories for children from low cohesion families and green trajectories for high. I can make those even more transparent if I'm not satisfied with how it looks. Right? Well, it's a little more clear here. Okay, so that is how you make a plot of your longitudinal model for a model that includes one or more predictors. And this can be expanded out to kind of any combination that you can think of. This basic code applies as long as you sort of extrapolate to whatever your particular situation happens to be. Okay, thank you everyone for sticking with me. I just wanted to end with a couple of notes on best practices for going forward for whatever you're able to take out of this session. Some things that I think are really important that I'm still personally working on in my own research. Number one is when you're running your models, don't jump straight to the model. Do what you can to plot your raw data as comprehensively as possible. So that you can get a sense of how your time trends might come out in your fitted data, and think about when you get to those fitted data, think about what elements of the plot you want to most stand out, but what else might be valuable to include that you could sort of fade into the background, right? Like having fitted trajectories over top of a scatter plot or over top of the individual values, the individual fitted lines. Another best practice wherever you can is to include uncertainty around your estimated parameters. It's too easy to have 2 or 3 lines on a plot and no sense of how precise the estimates around those lines are. So do what you can to get confidence bands or confidence intervals at selected points. I also recommend that you do include raw data in a fitted model plot when it makes sense to do that. So it'll depend on your situation, but that raw data can enhance the comprehension of the nature of your data and where those results came from. And then something that a lot of us are working toward is trying to make at least the materials that you use to get your results publicly available. So that could be organizing your plot syntax in a way that you could post it online, and you might also be posting your full data if that's possible, the code that you use to produce your results. Anything you can do to enhance reproducibility is a great idea. I've got a number of resources for you to scroll through on the back end of these slides, and I've found a lot of these useful myself, and hopefully these will be useful to you as well. So thanks again, and I hope you have a great time going through these materials, and I hope to see you again at a future conference. All the best to you.